On 9, we're given a reaction and a K, and we're asked for a Q. Take the moles, but for all three, but we need molarity. So moles divided by molar mass divided again by liters is molarity. This is a little bit more than they would actually ask on a real test, just because all this adding up of the molar mass is time consuming. But anyway, we should know how to do that. Put all those values into the Q math, products over reactants to the power of the number in front. That was a misprint in case your version still has that. So I corrected that. And we get this. Now my phrase is bigger is less negative, and that is definitely less negative. The power on 10 is less negative here, so that's bigger. This is smaller. Is the system at equilibrium? No, because otherwise Q would have turned out to be K if the system was already at equilibrium. And so which way will it shift? Well, we just said Q is smaller than K. That means there's too much denominator and not enough numerator. There's not enough product, so the reaction needs to go to the right. When you read through 10, it may seem that you don't have enough information because we put some in and that it's allowed to come to equilibrium. And that sounds like a real small amount of information. But let's take a think about what we've got, because they give us this reaction and you've got a solid and it becomes a gas. So when you use Kp, you're not going to use the solid. That's why this is all crossed out. Well, how much gas is coming out? Well, an unknown amount, right? But it's not like this is unsolvable. We can call this amount X. And if you get one of these, you also got one of those. So these amounts are equal. And of course, they started out at 0 because it only says that the ammonium chloride is placed in the closed vessel. So only this is placed in. At the moment they placed it in, there was none of this. So we start out with 0 here. We get some unknown amount. And then we know Kp. Well, Kp is products over reactants to the power of the number in front, except that the reactant is a solid, so we'll skip it, and effectively our denominator is 1. Then we can solve for X by taking the square root, and that is not the answer. And that is a way to effectively flunk this problem on the real test, because you didn't actually answer the question if you just leave it as X. You probably, I'm going to guess, you get 1 out of 2 points, which is a 50%. And it was the easiest of the 2 points too. So don't just solve for X, answer the question, which is what's the pressure inside the vessel? And the pressure will be the total of all the partial pressures. So the total pressure will be the pressure of this one versus plus the pressure of that one. I know they're the same thing, so they're both 0.8, and the total pressure will be 1.6. On 11, we're given a reaction and a K, whopping 36, which means we're not going to be able to just scratch out minus X or plus X when we do any K math. We're given moles and moles of reactant, nothing about the product, so that's going to be a 0. Notice it's in a 3-liter flask, though, so the molarities, which is what counts, of the reactants are divided by 3, so we get 0.06 and 0.06. So what are we looking for? The concentration of bromine monochloride and how much, and what they mean by that is moles, by the way. So we're going to find both in the end. So this has to slide to the right, which means if we make 2 of this, because we're going to make some amount, and whatever it is, it's twice whatever was destroyed of each of these. So we'll destroy 1 of these and 1 of these, and we'll make 2 of those by proportion, which means this is our equilibrium amounts. We're going to take those amounts and put them into the K math, products over reactants, the power of the number in front. And don't forget the squared term there. That 2 also turns into the power of 2. And what we're going to have here is a loophole, because we have the ability to square root both sides, because we have a squared term up top and a squared term on the bottom. And when we square root both sides, we can effectively take the square root of the numerator and then the denominator separately. So we don't have to know the final answer to square root it. So we can cross out the squared term here, and we square rooted the top. Cross out one of these, we square rooted the bottom, and of course the square root of the right side turns out to be 6. Then we have a mathematical expression which is back to sort of like middle school algebra, and we can solve for X. However, remember, X was not the answer, because it does not answer the question. What is the question? The molarity of BrCl. Well, the molarity is double X, isn't it? The molarity of BrCl is double whatever X was. Furthermore, they asked for the moles, and the moles would be the molarity times the liters, and the liters was in the 3-liter flask because this is a gas, so it fills the whole 3-liter flask. And molarity times liters cancels out the liters and gives us moles. So we get this. Now, to be fair, this is a little unusual for the real test. They probably wouldn't ask you both of these. And in this style, I don't think they would ask you moles usually, because that's just asking for wrong answers because kids misread the problem and they're trying not to get wrong answers for reasons like that. But anyway, it's good practice. On 12, we have a reaction and a K value, and it's more typical here, the E-5. And they tell us we have a certain amount of moles put in a certain amount of water for the reactant. Now, the most probable mistake is that kids say, oh, it's half a liter of solution, therefore it's half of 0.1 in molarity. But when you divide by a half, you effectively multiply by 2. And if you need to hit pause, I would do that because, oh my gosh, this kind of stuff comes up. When you divide by a half, you do not get a half. You get 2. So the starting molarity with this is 0.2. It's double the amount of moles that they stated. There were no products mentioned, so they start at 0. The reaction must slide to the right. One of these destroy generates one of these and one of those, and these are our equilibrium amounts. We put it into the K math, and here we can use our typical loophole here, where the K value is 3 decimals or greater smaller we put them into the K math, and here we can use our typical loophole where the K value is 3 decimals or more smaller than the molarities being used. Therefore, however much this destroys won't be enough to mathematically matter, so why bother doing something that won't matter and won't change your answer enough to matter, so let's just not do it. Plus, it lets us out of the quadratic formula now. And this happens a lot on the real test. Now I have something I can solve using just easy algebra, and X solves as this. What was the question? The hydroxide ion concentration. It turns out that this time X is the answer, but if you just solve for X, you'll mess up your score. State the answer clearly. And the capital M is kind of belt and suspenders method, probably because brackets means molarity, but why not throw it in? I have here a little bonus section based off of problem 12. If we've determined that the OH minus molarity is 1.9 E negative 3, then roughly speaking, what's the pH? And this is something that the test writers do expect us to be able to do in our heads, and they might write this as a multiple choice problem. Again, you don't have to do it exactly, but you do have to be able to do it roughly in your head without a calculator. So then what would be the pOH of this? Well, it would be negative log of the OH minus molarity value. Well, I'm not expecting us to do this without a calculator exactly, but what if it was 1 E negative 3? Then it would be negative log of 1 E negative 3, and that would be positive 3. However, the molarity was a little stronger than that in the basicness and its OH minus quality. So that means that the pOH is not 3, it's a little bit farther down. Remembering that a pH or a pOH scale is stronger in the value of the thing you're measuring if you go down toward 0. A more acid solution is not above 7, it's under 7, and a stronger pOH value is not going up, it's going down. So this value for the negative log of is actually a little under 3. Because this is stronger, the pOH value goes down. And so when we try to find pH by subtraction, we do 14 minus 2 point something, not 3 point something. Remember, this went down. And so we're going to get 11 point something. And so the pH value is between 11 and 12. Also, I find that some kids don't have much practice in using decimals and dividing by fractions like this. If you have 6 over 0.2, they really do think that you know that that's 6 over 1/5, and that when you divide by a fraction, you multiply by the reciprocal, and that you can do this in your head, and that 6 over 0.2 is 30. So we need to get good at these kinds of dividing with fractions also. On the old AP problem, we've got quite a number of things to do. The first one, though, is just write the KP expression, products over reactants, the power of the number in front. There's not much to that. Find the Q value. They gave you the values. We're just going to put them in. Don't forget the exponents. The 3 and the 2 become exponents, and we get this value. So which way will this shift? Well, if K is this and Q is that, this is very definitely larger, which means we have too much numerator, which means we have too much product, and the reaction will shift in the reverse direction or to the left to compensate and make the K become true. They gave us Kp and now they're asking for Kc. So we go look up the formula that converts between the two. Don't forget to use the correct R. It's the one that has atmospheres in it, and definitely not the one that has joules in it. Don't forget about delta N, and that's the change in moles of gas. And what we had was 4 changed into 2. So we lost 2 moles of gas. So that's a -2 is the exponent on that. So when they go and solve it like this, which is valid if you want, you could solve it before you put in the numbers, then that's a -2 exponent, which means you square the value, but it all lives in the opposite part of the fraction that you're looking at because of the negative number. So effectively what you get is this times the whole value of this squared. So this times this squared, but remember this does not live in the denominator because of the negative value of the exponent. It lives up here. So we take all that, and when it was squared, and we multiply by this, and you get 1.02. And remember, there are no units on K, because I know in some other part of the workbook they left units on this, and in fact they left the units on K, which is wrong. They left the Kelvin units. There are no units of the constant Ks, and so you cannot leave the Kelvin units in there, and I wish they would quit doing that. Now there's some real trickery going on with D, and it is a bit of a booger, and I had to actually sit and think for a moment again. With I, though, that's sort of the easier part. They're asking for the K value. Well, they gave you the K value for this, and this version is just this one flipped end to end. And so all the products become the reactants and vice versa. So the numerator becomes the denominator and vice versa in the K math, which means we get the inverse of the previous K value. So we're going to take the inverse of that, and we get 120. Now, the part about double I is I really had to sit and think. So what they don't tell you is that this is the combination of 2 previous stated equations. Now, one clue that's in there, but of course they don't say it, is, look, there's N2 and H2, and that's not in any of this. It's back from up here. So we're going to take this equation, which I rewrote here, and combine it with something else, and when we do so, we'll make one of these. So here's my N2, 3 H2s, and notice the ammonia is missing. So something canceled out the ammonia. Well, if we use this version, the ammonias would add up. It must be this version. Notice also the H2S is on the left, but it doubled. This is on the right, but it doubled. And look, that would mean that this is on the left, but it doubled, which would cancel out 2 NH3s on the right. All that is to say that we're going to use this version, but double. And that means we get the K value of that, and we square it. What did we do to this one? We didn't do anything to this one. So we're just going to borrow the K value from the top, and it's this. And then combined half reactions, then have their K values multiply. So we're going to take the value of this one and square it times the value of that one from the top and multiply it in, and we get the overall new Kp.